Okay, I think we will get started here. Um, yeah, I've enabled screen sharing, so Molly will be presenting the uh, DIT paper today. So yeah.
Oh no. Okay. Should I go ahead and start?
Yeah, we can see your screen and everything. Yeah.
Okay. So scalable diffusion models with transformers. So diffusion with transformers. So we start with this is just we'll go into each of these in more detail later on, but just to give a start, we start with a noise latent. So this is from the VE and latent diffusion, for example. So we will be working in latent space. We patchify it into a sequence of patches, the sequence being what the transformer will work on. The DIT block has is transformers. It comes with so there's also conditioning. The time steps are sinusoidal, and the labels are like lookup embeddings. The labels being turned off for classifier-free guidance half the time. A layer norm, and then to get it from the hidden dimension of the transformer back into the correct size for our output, there's a linear layer, and then just reshape it into the shape of our output. So as I said before, the input, so for the latents that we'll be using, it's channels of 4, height by 32, width of 32, so I is 32. So it's, say if the patch size is 4, for example, it would be 32 divided by 4 is 8. So we would have a sequence length of 64, for example. And then here is the patchify portion. As I said before, we'll end up with a sequence length of 64. I chose a hidden size of 1152 because that's what I copied from the code. Yeah, so we just project from whatever our original channels were, so 4 to the hidden size that we want to work to, which is 1152. Kernel size is whatever our patch size is, and stride is our whatever our patch size is, so it's non-overlapping patches. And yeah, I just show that when we go from a 32 by 32 by 4, we end up with a 64 by 1152. Yep.
Are there position embeddings for the
Oh
in the
yes.
Pacify or something?
I wait. I did not see those actually. I would expect there would be. And now that you mention it, I'm wondering why I did not see them when I looked at the code. Position embeddings were not mentioned. Oh, I see. No, MLP wouldn't have it. Attention wouldn't have it. That is a good question. I did not see it when looking through the code. Huh. I should have thought about that one, or I think I did think about it, and then just didn't see it. Huh. I'm not sure. Yeah, when I looked through the code, I didn't see them right away. I'll have to. So that is odd. I didn't see them when I was looking through. So, oh, I'll have to look at that. Oh, what were you
There's a
saying?
comment. There's a comment here saying, I guess in the paper it is mentioned that they have
Oh,
a standard positional embeddings, sine, cosine.
Ah, okay, thank you. Yeah, so standard VIT, frequency-based positional embeddings. Okay. I just must have missed that as I was going through. Yeah. Thank you. So standard positional encodings. I think I did see the standard positional embeddings. Yeah. I'll just move on then. Thank you for that one, Ali, I think. Yeah. And then, yeah, so next, no, yeah, no, thank you. Next, there'll be a pointwise feed forward and multi-head attention. There's adaptive layer norm 0, as shown here. We essentially want to generate some scaling and shifting factors. Let's see. So we have two norms, an MLP and an attention. And then this is what generates those scaling factors. So we just go ahead and generate them all. There's 6 in total, as shown in the diagram over here. And then after we generate them, it's just our input normalized times our scaling factor gamma, and then shifted by beta, sent through the multi-head attention here, multi-head self-attention. And then that is multiplied by a scaling factor again in alpha. By the way, these are all set to 0. So the result of all of this operation on the very first batch will just be x is x. And this is essentially to allow the residual to be 0 to start off with, so it can shortcut through the entire network. Let's see. After this, we normalize again, we scale by the second gamma, shift by beta again, same pattern. MLP for the pointwise feed forward. Alpha again, so it can go to 0, and we can just pass through, and then that's the end. Yeah, we standard sinusoidal embeddings for the conditioning, as we saw in other papers. That's how we get an embedding for T, and then the lookup embeddings, which for this is class labels for ImageNet. I believe everything in the paper used ImageNet at either 256 or 512. Maybe there was smallers. I don't remember. But lookup and embedding for that particular class, and then a dropout of 50 for classifier-free guidance on that lookup embedding. And then the two are just added together for the conditioning. I just used a random variable here just because more code and we've already covered it. But yeah, the output is the same shape as the input, as we would expect with transformers. Okay, moving on. And then what we're trying to do next is just get it to the correct output shape. So we're going to generate beta and gamma for adaptive layer norm. This is not adaptive layer norm 0, just adaptive layer norm, so it's just beta and gamma without the alpha. We normalize scale and shift x one last time, which is sort of the layer norm here. And then we pass it through a linear just to reduce the number of channels to something that'll be reshaped into our output for our model. And then the output is just patch size times channel times 2, and we can probably see where that's going. And then for reshaping, we can see patch patch size channel. Just reshape it to be height, width, and then those. This einsum here is just doing the transposes. So just the transposes that are needed if you're doing regular PyTorch, and then now we just reduce the patch and height, and then width and height, or width and patch size here. H is used both places because they're equal, because this is assumed to be square images. And yeah, so we end up with, in this case, a patch size of 2, 8 channels, 4 for the noise, 4 for the covariance matrix, and 32 by 32, which is what we need for generating our final image. If you wanted to use L-simple instead, there was a variable that would change this into just outputting the noise alone, but I did not include that due to simplicity. Any questions so far? Okay, moving on. They also explored a few other architectures. So cross attention. So using cross attention, and they also explored just concatenating the conditioning to the sequence length of each block. But those both performed worse than adaptive layer norm. And then adaptive layer norm adaptive layer norm 0 performs better than regular adaptive layer norm. The 0 is that alpha before the residual connection. This is the result when this is what they got for various FID scores as they held the patch size constant. So yeah, as the model's bigger, it performs better. Even at the same number of training steps. Yeah, and as the patch size gets smaller, the model tends to perform better. It was interesting that at a patch size of about 4, they seem to be fairly close together, and 2, they also seem to be close together. But the XL model was much better. It seemed to be much better at a patch size of 8. Something I noticed. For model size, patch size makes the model perform larger, or smaller patch sizes makes the model perform better. And then again, I found that L and XL seem to be pretty close in these graphs. There is a difference later on, we'll see in charts. Let's see. So more G-flops. They did focus a lot on G-flops instead of parameter counts, and we'll look at why that is, or get that a bit more later. So as G-flops increase, model performance improves. They also did find at very large amount of compute, the larger models became more kind of compute efficient, so they just performed better when you got to these. Even if you controlled for compute, the larger models would surpass the smaller models at a certain point, at a certain amount of training. So that's something that's seen a bit with transformers. So I would think that would be expected. Okay. And then
sorry, could you go back to the previous slide, the second plot? Yeah, the plot on the right side to the 9. Figure 9 here.
Oh
just
yeah,
thinking,
yeah, there's an overlap.
Yeah. So they're thinking here, as the so 2 things, right? So they probably didn't mention parameter count. Is it the same kind of maybe it is not, but with LLMs, with a chinchilla model versus a really large model like Palm. They found that chinchilla did better because they found the right ratio of data set to the number of parameters and some tuning related to that. But Palm was 540 billion parameters model, and yes, it may have done better than Chinchilla. I don't recall which did better, but for the equivalent sizes, Chinchilla did much better because of the way they understood the data set to parameter size ratio. So given that, once you know that, then it's more about more epochs or more controlled training rather than which may still yield the same number of gigaflops, but the parameters count is less. And I just wondering if there is any of such discussion or correlation there in this at this point when you mentioned that they or when they have decided to focus on gflops.
Yeah, so they're focusing on gflops as opposed to parameter counts, and we'll see in a bit the difference between how it performs on, say, compute versus FID as opposed to like parameter count versus FID in some of the next slides.
Thank you, Archie. Great.
Yeah. Yeah, it's to give as of right now, giving an overview. Specific numbers are a little bit, yeah, I'll be showing next. And then let me know if that fixes or does not, or answers or does not answer your question. Let's see. Oh yeah, you probably saw this note at the bottom for parameters. So yeah, the parameter, so DITXL, which was a bit, it's like 600 million parameters, and LDM's like 4 million. We'll see exact things in a few next slides. But yeah, it performs better than the latent diffusion models at 256 by 256 by what seems to be a fairly significant margin here. And then also at the 512, and this is the, which one is this one? Diffusion models beat scans paper, I believe. Yeah.
I have a maybe rather simple question. So what does precision and recall over here means? I can understand, FID, IS scores, but just wondering what would precision and recall in this context mean?
In this context, I'm not sure.
Yeah, I mean for this benchmarking, is it like this is?
It's when they have a classifier for the images. So I guess they produce images of different classes, and then they try to take an existing like inception classifier, and then they're measuring the precision and recall on that with that data set. I think something along those lines. It's just measuring. It's just measuring if it's being able to produce the correct class, and if it's like in realistic images of that particular class. Kind of. I think that's kind of the goal of those metrics.
Okay, so it's not supervised. It's like another
It is.
model.
It is supervised. Well, it's using a classifier, I guess. So.
Okay, not human supervised.
Yeah. No. There's no humans that are involved there. Yeah. It's. Yeah.
So the score is as good as the confidence we have in the models that are scoring it.
Yeah. I guess so. I don't remember exactly what models they were. I think they were inception models. It's discussed in previous papers.
Thank you.
I thank you for pointing that out. I need to read that just to know exactly how that's done. Okay, so that's, yeah, so they performed very well by comparison to late diffusion and the diffusion models beat GAN's paper. Okay. these were some graphs where they showed the size of the circle is the amount of G-flops. So more G-flops, it performs better. And then this is G-flops by comparison to this is for guidance, which I did not find charts for guidance that were that good for LDM or I did find them for LDM, but not DIT. So I couldn't do a good guidance comparison. Just going to point that out before we get to the next ones. But they found that it performs better than both of the latent diffusion models, and had a bit more, and we'll see this in a bit more compute than LDM4 or latent diffusion models. Let's see. Oh yeah, and here's a flop comparison. This is what I mean by a little bit more. So 118 gigaflops versus 104 gigaflops for LDM4. The exact score for LDM4 is sadly on the next slide, which is 10.56. So 10.56, 9.62. So it gets a better fit and uses a little bit more gigaflops. The next one is parameter
So can you
efficiency.
put back to that? So you think, what? Wait, what are the difference? Maybe let me just see. What is the difference between the first row and the second row? It says there's more training steps.
Yeah, more training steps.
But if it's training for longer, shouldn't the gigaflops be different?
I think they're controlling for oh no, they should be. I think it's gigaflops of does this gigaflops do one pass through the model? I think it's gigaflops do one pass through the model. No, that wouldn't make any sense. What? I don't think so. Those are scale of gigaflops. I don't know how many flops
Is it just
are
a is
normally.
it just a inference thing then, or?
So they're suggesting throughout the paper to measure model complexity by the number of gigaflops a model takes.
Okay, so
I believe that's it.
it's just an inference
It's
thing then.
right. I remember now. It's forward pass times 3, I believe, is what they're considering this number. So assuming the backwards pass is takes twice as many flops as the forward pass, I believe is how they calculate it.
Okay, but so if it is that, but it's just should be, if you're training longer, you're using more gigaflops. So I'm still confused.
Yeah, I think this is, let's see, where's training? Yeah, so if we're training, let's see how many. So this is like what here is like 10 to the was it 10 gigaflops? Then wow, that doesn't make any. Huh. Interesting.
Yeah, it could be the inferencing time because whatever. It still doesn't make sense, right? Why would we put the gigaflop number and the training steps and that does not match? Even if it's inferencing time.
Yeah, I'm looking back here at the what is it? The very first one for XL is all the way over here, which is a little bit less than 10 gigaflops, which wouldn't make any sense. Huh. That is interesting.
I think it's probably just for the inference maybe.
I would, yeah, when I looked at the paper, if as long as it was the same model, they always had the same flops, which is why I made the assumption that it was just inherent to the model, even when the training steps changed.
Will it be these many gigaflops? Inferencing is one step, right? Or one pass.
Yeah, inference would be, yeah.
So, but then would it be 118 gigaflops for one inferencing pass? Or whatever the batch size, one batch inferencing pass, whatever it is. That seems too high, right? I don't know.
Yeah.
I mean, maybe you guys know.
I've never counted flops before, so I'm not sure what the scale should be.
Yeah, me neither. I'm not sure either. It does seem high, but I don't know. Um, I mean, in the paper they talk about the models in terms of gigaflops, so I
Yeah,
suspect it's just like increasing transformer forward past gigaflops. I think they're just talking about, yeah, the inference maybe.
yeah, yeah. I saw somewhere that it was something like inference times 3, assuming 2 was the backwards pass was 2 times the forwards pass. But yeah,
Okay.
that would be,
Okay.
that was just the assumption I went with, and didn't actually notice that the numbers don't seem to line up for some reason. Interesting. Thank you for pointing that out, actually.
So I haven't looked at the paper directly, but I asked Bing GPT and it has a pointer to that paper and it says the inference step of DIT takes 0.5 gigaflops per 256 by 256 image and 2 gigaflops, which is exactly 4 times for 5 to the 512. But I'll check the paper also and see if they have. But the reference is right. It's not, at least the reference was not hallucination. I don't know if the answer was.
Interesting. Yeah, okay. We'll move right along. The next one is parameter efficiency, as I was talking about before. So the number of parameters for latent diffusion was around 400 million. And then the parameters for DITXL is 675. So more than 1.5x increase in parameters. And then the FID is, what is it? It is better for DITXL, but DITL, which is closer to the number of parameters in latent diffusion model 4, is it's closer to that. And yeah, latent diffusion models 4 performs much better than DITL. So the training steps was very low here, which makes me question that question what I got, but this was the closest thing I could find in their paper. So I feel like 400 was probably more of a sample model they had. But yeah, I wasn't able to find a longer trains DITL, so in the paper.
So how many training steps did they train the? Oh, it says. Okay, so for the LDMs, it says there's 2.9 million steps that they trained for and 178,000 steps. Is that right?
Oh, here, DTM steps. I think that might be. Oh, I'm not sure actually. I think it might be 2.9 versus. I don't know. So the problem with this graph is I got this from the latent diffusion paper and I got this one from the DIT paper.
Oh,
so
okay.
there might be some differences there as well. That's why the graphs
Okay.
are completely different too. So,
Okay.
but I just wanted to point out the parameter differences. That's mostly what I was going for.
Yeah.
And I was not able to find class conditional performance comparing parameters. I only found class unconditional, where I could directly compare parameters. So does that answer the question from before, out of curiosity?
It's kind of related, but it's not the same approach for the parameters to scaling laws, if you may, but it's related. Of course, they're pointing out that transformers scaling is better, but it's not like this transformer architecture versus that transformer architecture will scale better.
Oh, I see.
When I like that's what Chinchilla versus Palm is. Those are both LLMs. Both uses similar encoder only or autorecursive transformer models, but there the claim is that it's the size matters, but efficient detection of what size will matter. After which it's not really very helpful. And so if you add more layers, then yes, you need to then do something to the dimensions and so on and so forth. But there's some kind of formula they come up with, or some kind of law they come up with of how to scale so that your data set efficient as well.
Okay. This was done for this paper. All the experiments were done on either, I believe, they were all done on ImageNet, and some of them were done on 256 by 256, and some of them were done on 512 by 512. I'm not sure if there was a size smaller than 256 by 256 at the moment.
Yeah, I mean, it's a different thing, but the reason to bring G-flops makes sense in this context, the way they are explaining it though. Thank you.
Yeah. Thank you for the questions. Yeah. And then next, this is just their smallest models and then their patch sizes. So what is it? This would be large, this would be XL. These are the two smaller models than L. And then patch size of 8, patch size of 4, patch size of 2. And then as you decrease the patch size or increase the transformer size, the performance of the model improves.
Why is the dimensions of the images different? I don't know. Maybe they didn't. They probably didn't explain why, but I'm just noticing this.
I think that might have been a copy and paste thing. I don't know. Not sure actually. That's
That's
interesting.
really weird.
Yeah, I think it's I tend to believe what you answered, only because I mean at the very least H should be same as W.
Yeah.
So it probably is a copy paste or not paying full attention to the images versus other things while publishing
I hope
papers.
so. I hope so, because this is kind of, yeah, it's kind of weird. I don't know what.
The other thing that I was also wondering was, they did tons of experiments, which is pretty good and useful. But all these, the authors are from universities, and each of those experiments definitely took days to do, or maybe the longest one took days. So it's also both interesting and good to see that non-industry or from universities are seeing some papers which are dealing with these large, not billions still, but yeah, large models.
Yeah, I think they were also trying to make a case for we could scale this up in the future, and it has would have some nice scaling properties and that variety of thing. So similar to how we see in NLP. Yep. Oh, and then it's just any questions here, and then some more samples. So. So any last
Yeah.
Yeah.
I guess just overall I'm not as convinced about this being better than the units. I don't know.
Yeah, for this paper, I came to a similar conclusion. You use more parameters to get similar results.
Yeah.
Yeah. But I think there's simple diffusion and as another one to look at to see how that one performs, for example.
Mm-hmm.
So, yeah, I think this was just what was it? quote unquote first attempt to get something similar to what UNets were getting. So and they got
Mhm.
state of the art. So, but yeah,
Yeah.
more parameters to get state of the art. Yep. And yeah, they just show a few that they find they found adaptive layer norm to be good. A lot of the code base is pulled from the GAN what is it? Diffusion models speak GANs. Same code, so a lot of that. As far as implementation details.
Yeah, one of the things is that the latent diffusion, I think they use a cross attention, so that's it. And I don't know. I think they got better results with the cross attention. So that's interesting that they are seeing here that it did not get as good results. So yeah.
Also, I think one of the criteria is also to kind of find the correlation between G-flops and commons, and then to prove that it is better. And somewhere I saw in the paper they said with cross attention they had 15% more G-flops, and
Yeah.
Okay.
Yeah.
That was another reason.
Also,
Yeah,
it would be
like for
important
example, how would
point-wise.
you use this then to like? Because I think the nice thing about the cross attention was it allowed for conditioning on more diverse types of input. So like, how would you do this for like text, for example, or other images or something like this? Like with a cross attention, it was fairly easy to get that to work. So that's what I'm curious here. Yeah, I guess we should probably look at simple diffusion as well. I think they trade
Yeah.
some like text conditional models as well, if I
Oh.
recall correctly.
Uh,
So
yeah. One of the reasons I presented this one is I was going to sign up for simple diffusion. So.
okay, okay, yes, we could talk about it that one as well. Um, yeah, like, yeah, they have some. I'm looking at the simple diffusion. They have some text conditional models, and I guess how do they do that? How do they use text conditioning? Text to image, um, UVit. Let's see here, appendix. Not entirely sure. Can't seem to find it from a quick glance, but I don't know. There must be some.
So I did. Can I go back to that gigaflops from the paper?
Yes, I am very curious what those gigaflops are now because I thought I knew what they were.
And if it's not too much to ask to put the paper, I can tell you exactly which section they talk about, page 8, and that's where the reference is. So I think this number correlates 118. I think it correlates with 400K training steps. That's what yeah, so right there on the bottom left. So to investigate this further, we plot the FID 50K at 400K training steps. So the gigaflops are, I'm assuming, after training steps, not the inferencing time, based on the statement. That's how I gather, but do others see the same or differently?
Oh, transformer G-flops versus training compute G-flops. And figure 8 would be training compute G-flops. Or sorry, transformer G-flops. Oh, I see.
Yeah, so 10 square is, oh, so then it is transformer G-flops is inferencing only.
Yeah.
Because that's just the transformer. Yeah, oh, wow, that's pretty high. Because 10 power 2 is 100 and that's 118, right? In that other table that you had. which is where it matches somewhere
And you
there.
can look at the
Oh,
range
yeah.
also as the range for the training compute G flops is much higher, like 10 to
Yeah.
the 10, 10 to the 11, so significantly.
Yeah, significantly higher. Yeah. I
So yeah, it
thought
has
these
to
were
be
the same.
inference.
I read this a few, like, many times. I did not notice these were. I was like,
Yeah, and
wow, why are they doing such short trainings?
thank you for yeah, allowing that question in the middle of your other discussion. I think that clarifies a lot now for
It
future as well.
clarifies a lot for me, actually. I don't know how I conflated those two the entire time.
So yeah, that one is looking at G flops of the inference, the other one is looking at G flops of the training. Yeah. Okay.
And that would make sense why the blues were essentially completely overlapping here, and the greens are. There's only. Oh no, they're not completely overlapping. Okay, never mind.
Because they have both. They're looking at different sizes, but they're also looking at different patch sizes.
Yeah, yeah. Oh no, I for some reason I thought there was supposed to be like 12 blues on the thing. Sorry, my mind. Yeah. Yeah. And
Okay.
then flops over here, and that lines up with this graph. Yeah.
They should have put the flops of the UNet. Is there any plot that's showing both the transformer flops and the UNet flops?
Uh, the closest is that one at the very beginning, which wasn't. This was the best I found that actually showed it, and then I pieced together
Okay.
my comparisons.
Okay, so in this one, oh yeah.
Yeah, so if I go to the very end, the appendix had this big table, which is where I pulled most of my information, or I
Yeah.
pulled mine from. They did have this, which is where I pulled the G flops for the
Yeah, so
latent
that's the
diffusion models.
unit, right? Because that's what LDM unit. That's what
Yeah.
the heading says.
Yes. Yes. Yeah.
Yeah.
They're all those are UNets. The
Yeah,
ADM is
all
also
these are
UNet.
units. Yeah. But they don't have they don't have what is it? Well, oh yeah. These are all units. And yeah,
But yeah, they're not including the flops from the they say the flops for the DDPM components. They're not including flops of like the VAE or something like this, which I guess it's pretty trivial because when you're doing multiple steps of the UNet, then the VAE one is probably not as important.
yeah, I think I don't believe in anything they measure the VAE.
Oh, because are they doing this in latent space also?
Yeah, everything's in latent space, so
Oh, right. Okay. Wait, anyway,
yeah.
that's it. Yeah. Okay, that makes sense.
Well,
I
except
think
this one, I think.
Yeah. Yeah. Okay. Okay.
so. The other thing is, if you go right above, there's table 4 on this page.
Table 4. Table 4.
Yeah.
Oh
Yeah. Oh,
yeah,
it
this
was
one.
right there. Yeah. Yeah. So,
Yeah.
and then they did mention that the cross attention performance, like you look at the far right, for a DITXL2 is quite much worse compared to the bottom, well, yeah, bottom two, those ADA, not linear normalization to yeah, adaptive, yeah. So
Is it
I wonder, you know,
it's most comparable to this one, right? Maybe?
yes, but
Yeah.
essentially 2 points, right? So, and in fact, if you compare that with cross attention um, with LDM, did they have the FID number for those? For the table 6, they just had the gigaflops. They didn't have the do they have FID? Yeah, they don't have the FID numbers.
Yeah,
No.
I had to pull those from the other paper actually. So, yeah, from late diffusion paper, and I don't know if
Okay.
those match up necessarily. They seem to line up about where they should be though. So
Yes. So I think to Tanish's point, cross attention is what would be a more
Mhm.
useful or more commonly used scenario currently, right?
yeah,
Or the guided image generation, right? Rather than just a random image generation from the latent space.
yeah. There is also a parameter difference. So what is it? This 598 versus 675 for using cross attention versus Adeline 0.
Wait, so we have cross attention
Yeah.
is 598 and okay, and 675. Okay.
hmm
But interestingly, Adel Ellen, that one is just 600. Wait, what? Why is there a difference there? I'm wondering.
An extra alpha parameter before the residual, I believe, would be the difference. Yeah.
Okay.
So the difference between the two is, yeah, it's this alpha parameter right here. I believe
Okay.
is the only difference,
And
or the MLP to generate that alpha. But yeah.
right. Okay. And
Yeah, actually,
so,
page 3 has the all the 3 images. If you want to look, page 3 of the paper. Sorry.
Page 3 of the page 3 of the paper. Okay.
Yeah, which I think you also had it in your presentation also, but yeah.
Let's
Yeah,
see.
right. You
Page.
just crossed it.
Wait, page 3.
Yeah.
You said.
Yeah, you just crossed that little while ago.
Okay, up or
Is this
down?
page? Oh,
This page 1
let me.
here.
so this one
Yeah,
is
keep
page
going
2.
down. Yeah,
So
then the right below is page 2, and then the next one, the top of the, yeah, that's the one. Those are 3. Is that
Oh,
what
the
you're
3
looking for?
architectures.
Yeah.
so Ada Ellen 0, but they don't have one. But I was wondering, Ada Ellen versus Ada
Yeah,
Ellen 0. That's what I was curious about.
yeah. And I'm
I
saying
thought the
it's
only
just this
difference with
alpha.
that, but I thought the only difference was that it was initialized with 0.
Oh,
I thought that was the difference between Ada Ellen and Ada Ellen 0. So I thought the parameters should be the same. That was my original understanding of it.
yeah. We also regress the. Yeah, we modify the Adeline DIT block in addition to gamma and beta. We also have a regress a dimension-wise
Oh,
parameter
okay. So
alpha.
they are adding a
So,
new parameter there.
yeah, yeah.
Okay, that makes sense. Then they should have put that as another block design in their thing.
Oh, with
You know,
that graph up there, yeah.
yeah, they should have put it as a separate one there because it is different. I thought
Yeah,
the architecture has a slight difference there. Okay,
yeah.
okay, that makes sense. Um, okay,
I think it was similar enough they were running out of space, so they cut it.
yeah, maybe. So yeah, if you go back to that, I guess it was page 2 with the of
Oh,
the
page
paper.
2.
Yeah,
Sure.
I guess that's the one that has the comparison with the units, right? So here it's
Yeah.
saying you have F. Wait. Wait a minute. Okay, so what's the x-axis?
It's not model architecture, I think.
Flops. Okay, that's weird. Okay, why don't they just put an x-axis? I don't understand. This is weird.
It would be easier to see what was happening. I think if
Yeah.
they had an x-axis.
Yeah, so they're
I've
just putting the size of the bubble is the
it's the G-flops, yeah.
yeah, okay, I don't like this at all. Okay, yeah. They should just plotted the FID versus the G flops. That would have made I feel like that
Yeah,
made more sense. Okay,
yeah,
so they're saying here that they are having less G flops, um, but more yeah, less G flops and better performance than LDM. Okay.
yeah. Well,
Um.
I thought the same, but I actually found this was slightly bigger than LDM4, so just slightly.
Oh. Okay. It is slightly bigger. Okay.
In
Interesting.
G-flops, yeah, in G-flops slightly bigger.
Mm. Okay. Okay. And yeah.
Which is why I brought out those charts.
Yes, it's okay. And we don't know, like, I guess, yeah, so, and LDM4 was trained for, like, what was, they said millions of steps or something like this, right? How many steps was that trained for? LDM4. I guess you didn't have, it wasn't here, it was in your presentation, I think. Because I don't think they
Oh,
put that.
maybe they didn't. I have to remember. I remember what I got from
Yeah, here it
the
says,
late diffusion paper.
LDM4. Oh, yeah, it was right there. LDM4
Here.
was trained for, no, in
Oh,
the
here.
tables. Yes,
This one.
so it was trained for 178,000 steps. Okay.
Oh yeah.
But it has 400 parameters versus their thing that has, again, 675 parameters. Okay. Okay. So again, their point is like, so yeah, I guess that's really trying to say that the G flops, they're more efficient in G flops rather than parameters. Okay.
Yeah,
And
and the G flops over here. Yeah, that's the G flop 104 and 118.
right, right. Okay. And are they using guidance in their models? Because the other ones are
They
labeled with G for guidance, but
do,
theirs is not.
but they had less charts using guidance.
See here, for example, it
Spatio.
says no guidance.
No guidance, no guidance. Yeah, no guidance. These LDMs I specifically picked out because they had no guidance. Yeah, for
Okay,
the
so
late
you're
diffusion
saying
model.
that these ones here that you're showing have no guidance.
Right.
Okay,
I
and
got
so that's why you're saying it's comparable. Okay.
yeah. There could be some differences, but yeah, that I'm not accounting
So,
for, but close.
yeah, table 2 may have, again, it's kind of some information here and some information there. So table 2, and you may have had it in your presentation also, I do not recall. But in the paper, table 2, which is page 9, section 5, I think page 9, top left.
Table 2.
Yeah, so there they have this class conditional guidance 1.25, 1.5. Is that what you're looking for, Pranav?
Yeah. Okay. So you have. So they do are comparing. Okay. So they have a comparison without guidance and with guidance. Okay. 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 And so it's a without guidance. LDM4 is 10.56, whereas theirs is 9.62, and with guidance it's 3.60, and theirs is 2.27. Okay.
Yep.
And that's for 256 by 256, and the one below is, and there they do not have LDM
Mm-hmm.
in table 3 below.
Oh, table 2 below.
Table 3, yeah, right there. Yeah. They do not have
table tree.
LDM. Yeah.
Yeah.
Okay, so this is for this one is 256 they have, and they don't have for. Why is that? I wonder.
The latent diffusion models, I believe, only reported on 256 by 256 original paper.
Oh, really? Okay.
Yeah, I looked for the exact same. I spent a bit of time looking for the exact same thing. So
Okay. Interesting. Okay.
And there's now open source model, I guess, LDM model,
yeah.
because the projects, including Stable Diffusion and all, they can generate bigger images, right? So I'm assuming there are models out there which can
Mm-hmm.
generate them. Yeah, but maybe not
By
in
the way, what
open source, or
is?
maybe Hugging Face has those. But anyway, go ahead. Yeah, go ahead.
Oh, I was going to say what is CDM? There's a CDM there. I don't know, in table 2. I'm just curious what it is.
I didn't pay it. I didn't look, but it was 20, I believe.
Oh, cascaded diffusion.
Cascade diffusion. Yeah.
Oh, I don't think we've talked about that paper yet. Actually, maybe we should. Oh, okay.
I recognize the title.
Yes, yes. They
But
were.
yeah.
I think it was a state of the art paper for some time as well. Um. Yeah, I'm curious also like how this works with some smaller data sets as well, because I think transformers are typically known for you usually have to train them on fairly large data sets or yeah, I don't know.
Yeah, I mean they are. Yeah, they only train on ImageNet, so I'm not sure
Yeah,
about performance on smaller ones.
yeah, they do everything on ImageNet. Okay. And do they use some GPUs, TPUs? What did they use to train their models?
That was in here. Um, let's see. Conclusion, scaling. I know they use TPUs, I believe.
Okay, okay.
Where is it? Might be in there.
It may be like in the appendix or something.
I know it has pod. Maybe I can find a pod. It might be in the Ah,
There we go. Okay. TPU V3 pods. Okay. Those are old now. Now they're on to V4, V5. So it's like okay.
yep.
And they use EMA. They use all these other classic things, I guess.
Yeah, yeah. Yeah, they use EMA. Most of their settings, all of them are it's the default. I believe it's mostly all the defaults from diffusion models beat GANs. That paper.
Mm-hmm.
They mostly use the defaults from there. And they use a lot of
Okay.
that to set up their own model training. So
Yeah, I mean, table 5 had some ablation of some studies there, if you're interested. Yeah. Table 5
Table
is on
5,
page 13.
okay.
13, okay.
With one hand. Is this it?
Oh, that's just for the decoder, I think.
Yeah,
I
for
don't
the
know, that
decoder.
doesn't seem right. Did I get the wrong table? I think I got the
No,
wrong
no.
table.
Maybe I may have misunderstood. I thought you were looking for different sampling.
Oh, different sampling, I see.
And which one did they report? They reported
EMA,
the
I think.
okay. And did they use that for all the models that for the LDM models? Did they use that as well? I don't know if they did.
Yeah, F8, F8 version. Yeah, I think I'll maybe try to the Yeah, right there on the bottom.
Well,
On
they
the
said that
bottom left.
here. They said okay, it says we monitor metrics for scaling analysis using the FT-MSC decoder, and we use the FT-EMA decoder for our final metrics reported in tables 2 and 3. Um, okay. But I guess my question, it's unclear if for the LDM models, whether they or not they use these decoders, because they can use the same decoders for the LDM models.
So in table 2 and 3, didn't you just say that they used FTEMA decoder?
It's right here in the appendix that Molly is showing.
And sorry, what's your question, Tanish?
Oh, I was just wondering if they they use the if the LDM models that they had utilized these other decoders, because you can take the other decoders and use it with the LDM, but it's not. I'm not sure. Because
Yeah, so table 2
they
and
report with the FTEMA decoder, but then shouldn't they also be reporting the LDM models with the FTEMA decoder? That's what I'm
yeah, so
wondering.
table 2 has all the models results,
Mhm.
and including LDM. So assuming it's the same one for all of those, the
Yeah,
decoder.
yeah, it's unclear, but yeah, sure.
Table 2.
Yeah.
Oh, but we're not sure the decoder that we used, I see.
No, but
Yeah,
they say in section D, right, that we use the FTEMA decoder for our final metrics reported in tables 2 and 3.
yeah, but they use that just
But
for the DAT. Do they use that for the LDM models?
Uh, I think somewhere they said LDM hours, which I'm assuming they implemented it or they did something to it. I don't know what hours mean.
Mm. Oh no, that was Molly's. You mean Molly's slide? She
Oh,
took
that's
that from
copy
the
paste.
LDM paper.
yeah,
Yeah, she
that's
took that
copied
already.
pasted from. Yeah,
Sorry. Okay.
I
Yeah.
I really wanted to compare the parameter counts, so I needed.
Yeah, yeah.
Yeah, I remember now. Sorry. Yeah.
Yeah.
Mm.
I think they said with the ablation they said okay with the original decoder it's 2.46, which is still better than the LDM, but then it's also possible. I mean it's I mean this is very pedantic I guess, but it's possible that if you use the LDM, then the new decoder with the LDM models it may be better. We don't know. So they should have done it both ways. That's all I'm saying. But it's not a huge deal. But it's kind of um, for to be extremely rigorous. That's what I would do probably. Just try to get the best results with the baselines as well. Anyway, I
But
think it. I mean,
even so, even
yeah,
so, let's say if it was the original for LDM, 2 point, what is the number they have? 2.46 in the table 5 that we were just showing versus 3.60 or any other number. It's 2.46 is also much better than uh, the LDM number.
yeah,
And
yeah. That's what I'm saying. I'm saying like, okay, yeah, that's fine. But then also like, technically, it probably would be more rigorous to also have the LDM with the EMA and see if that's like if it actually significantly improves the FID in any way. Um, but I mean, I think they show their point fine. But like, if you want to be extremely rigorous about it, that's what you would probably do.
right,
Anyway, I'm just being kind of pedantic and just kind of yeah. But it's not. It's yeah, just something that I noticed, I guess.
Yeah, I don't see anything else about it, so yeah, this just craps.
Well, yeah, it's good that they have some of these scaling graphs because we don't usually see
Yeah.
that with the diffusion models. So that's also like overall, I like that they do that because
Hmm.
I think there's only I think that maybe it's the AGM paper does it and the improved diffusion model paper does it, and I think those are the only papers I've seen that have scaling graphs for for diffusion models. So.
Yeah, there's a lot of graphs at the end to see how it scales and
Mm-hmm.
training
Oh, and they've
iteration,
got the
what
whole trading
training
losses.
looks like.
Okay.
Yeah.
Mm-hmm.
So
Okay.
I've definitely seen where that might be helpful if you were trying to reproduce the results, for example.
Yeah, yeah, exactly.
Yeah.
Yeah, that's definitely helpful, I guess. Yeah.
Yeah. And then all of the pretty pictures are at the very end. So a lot of conditional samples. Yeah.
Mm-hmm.
In
These
case
are
you want to
class
look.
conditional samples, right? Not
Yeah,
not
yeah,
the.
class. Yeah. ImageNet. So class.
This is very good. Thank you so much,
Yep.
and really like the flow and your whole presentation style.
Yeah, I'm looking at these pictures. They
Paper.
still, it's very interesting that these are supposed to be state of the art, but like, it feels like they're. I mean, I cannot really pinpoint it, but it feels like there's still like artifacts and things like this in these images. So I don't know. Maybe seems like there's still room to improve here, even though I mean this is supposed to be like state of the art, but it still feels like these look. I don't know. There's like some few like, yeah, minor like I don't know. Like the ear looks kind of like those ears look a little bit off, for example.
Which ears, out of curiosity, are you looking at
Or the one,
specifically?
I guess, yeah, the one in the bottom, maybe.
Bottom here?
Yeah, I don't know. I'm just trying to analyze them very carefully and see if I don't know. It just
Yeah,
seems a little bit. I don't know.
we can zoom in.
It just is. Yeah, I guess maybe it's if it's at a maybe because it says 256 by
Oh,
256.
yeah, I find that interesting. There's a bit of like oh, in this one I find it's a bit sharper than I would expect to see, but I don't or the line here is I guess
Yeah,
that's just camera stuff though. But the eyes are a bit
yeah. The eyes are weird.
the eyes are weird.
I don't know. Yeah. So clearly, there's a lot of room to improve, even though the FID is like what 2 point something, but it can still be much better.
Yeah,
Yeah.
I
Or
guess
even the
also the muscles are not like the arm isn't exactly properly or the front leg isn't exactly properly formed.
Are we
Probably.
sure this is the if I'm the the best performing model? What does the
Can check.
legends say?
That's
Just
a
to
good.
be certain.
Yeah, DITXL 2, 4 seems like it.
Okay, interesting.
Yeah,
Uncurated, classifier free guidance. Okay, interesting. Oh, this
yeah,
is also 512 by 512, not even 256 by 256. Okay,
yep.
interesting. Yeah, I'm kind of surprised. I feel like these seem to have some odd artifacts and like yeah, look at those like the legs of that bottom image. That seems completely off.
Oh yeah, yeah. You mean? I think I see what you mean.
Yeah, like yeah,
Yeah, I feel
I
like
don't know. It's
it's.
interesting.
Oh wait, what is that? Is that a?
Yeah,
Is that a? Oh my god, is this? Oh, that's so
just
annoying.
completely looks mangled.
I don't know if you're seeing this big PDF thing that shouldn't be there.
Oh yeah, I
can
see it. It's showing up, but I can still kind of see the image, but it's just like it's small. Yeah,
Oh yeah, yeah. Look at what is
yeah,
that?
exactly. That's what I'm saying. It looks a little mangled and like a little bit off. Yeah.
Yeah, yeah.
Well, yep. There's clearly room to
So
improve, I guess.
yeah,
Yeah. So I feel like yeah. I don't know.
I've
We should
broken my
have a
browser.
whiteboard. Oh, it's gone.
Oh no, it's
Anyway.
oh
Oh,
no,
now you
it's
brought
back.
it back. uh, I wonder,
I
like,
don't.
yeah, the stable diffusion. I thought we get better images. I feel like I don't know. We get better images, but maybe it's also these are smaller models, and like if you have more parameters, it'll be better. I don't know. Oh well, I guess
Yeah,
yeah,
more parameters.
it's certainly interesting. Well, yeah,
Yeah.
I guess
Okay. I think that's
if there are no other questions, or if anyone else has any thoughts or comments. If not, yeah, thank you again, Molly, for presenting this. It was
great.
a really good presentation, really interesting paper. Yeah, so we'll again have next week. Yeah, a presentation. We'll see. Maybe Molly will be presenting simple diffusion. We'll see. Um,
I was hoping to get 1 week between then.
oh, okay. We can
Maybe.
try to find another paper instead. That's
Yeah.
yeah. We can do another paper instead.
Yeah.
Um, okay. Well, yeah. I'll figure out a paper and yeah. See you guys all next week then.
Yep. See you next week.
Thank
Okay.
you.
Bye.